Okay, so let's consider a situation where we have two different factors. And I'm going to give a silly little example. You've kind of heard of the show American Ninja Warrior. And just look it up on YouTube if you haven't. And in fact, if you search my name on Google, you will actually find, more important than me, there's somebody who competed on this and they were actually had one leg. So a one-legged like Ninja Warrior is definitely higher up the Google search list than I am. So um, we've got like imagine I'm training for the Ninja Warrior. So I've got to actually do two things. So I've got X1. I want to have, weight training because if you look, there's lots of obstacles you need to hang from. And if you don't do any weight training, then I'll just fall off them and be terrible. And I've got X2, which is I'm going to use um, kind of do cardio and fitness training. So I'm going to have cardio training. Because again, if I have no cardio, I'm going to run out of breath and I'm going to fall off the obstacles after the first few obstacles. So I need to have both of those in order to be successful. And we can think of it in terms of like a little bit of a model. So if we have X1, and let's just have, is a member of 0, 1, where 1 is we do the weight training and 0 is we don't do the weight training. So it's a little set notation there. So where 1 is we do training, and the same below. Then we can actually write, our kind of dependent variable, which is y, which is our performance. And let's just do it simply. We won't bother with any sort of, in, interact kind of intercept term or anything. We'll have alpha times x1 plus beta times x2. But we also have something, let's just call it gamma. And I can't draw a gamma for the life of me. So squiggle, x1 and times x2, which is only equal to 1 if both are present. And the idea, if this value here is greater than 0, then we have positive interaction, i.e. there's an additional effect from both being there at present. So here, both weight training and cardio training. And if it's less than 0, then we have negative interaction. So let's just draw this in a little graph, and we'll use a few colors. So let's just write this. And the y, that's going to be my performance metric here. And this is going to be my x1. So this is going to be my, let's just look back, that's going to be my, let's just get a bit more of this in here. X1 is going to be my weight training. And I either don't do it or I do it. And then we have two lines for x2. So we'll have x2 equals 0 and x2 equals 1. And we'll give them different colors. Let's just make this one red. And this one, God, this is a horrible, like, Yeah, I'm not sure about. We'll make that rainbow. We shouldn't really have rainbow sparkles in a PhD class, but let's just go with that. And so x2 equals 0, x1 equals 0. We don't do any sort of training, so we do pretty terribly. We fall off the first obstacle. Now, if we do weight training, but we do no cardio, then maybe we don't fall off the first obstacle. We run out of breath after like 2 or 3 obstacles. So this is our performance here. Now, x2 equals 1, so we have cardio training, but we have no weight training. And in fact, that means, we probably don't do much better than we did before, because again, we're going to fall off like, an obstacle if we don't do any weight training. So we're going to be barely better than this one. But if we have x2 equals 1 and x1 equals 1, then we perform really well and we win the American Ninja Challenge. So you can see here that this is the positive interaction. If there'd been no interaction, then there would have been this fixed increase for there would be a fixed increase for having x2 equals 1, but it wouldn't interact with x1, i.e. this term, this gamma, would be 0. So I'd put 0. Let's just make sure I'm not on rainbow. 0 would be no interaction. And don't worry, you don't need to understand, the regression notation. It's just to give you an idea. But you can see no interaction. These two lines would be parallel. Now let's do another example. So imagine, I've won the American Ninja Challenge and I want to do some weight training. I want to enter kind of a weightlifting competition. And there's 2 different strategies. So I can do x1. And again, it's not present and present. We'll make this using kind of free weights. And x2 is I'm going to use weight machines. Okay, so let's kind of draw this here. So we have x1 is the free weights. And then the red line would be x2, or the weight, let's call it weight machine, equals 0. And let's just have a green. Let's get away from this rainbow sparkles. This will be x2 weight machine equals 1. Okay. So this time, and this will be my performance Y. So my performance in the weightlifting competition. Oops, didn't mean it. What have I done? Okay. So let's just draw. So imagine that I did, neither kind of weights, then I do badly in the competition. So x2 equals 0 and x1 equals 0. I'm going to be somewhere down here. I'm not going to be able to lift up the first weight in the competition. But if I do a lot of training, then I'll do pretty well in the competition. So there's two different strategies. Some people say free weights is better, other people say weight machines is better. And imagine that there's not much difference between these two strategies. So doing the weight machines and not the free weights would give me a similar to doing the other one. But doing both doesn't give me, it gives me maybe a little bit of incremental improvement, but maybe I overtrain a little bit and get tired out. So we have this as opposed to this. God, these lines should be straight, sorry. And you can see here that the lines are kind of less than parallel. So that would be an example of a negative interaction. Now, imagine that if, doing both weights had actually led to a decrease in performance, I just overtrained, then we would actually get something like, I'm not going to write everything out again, but we'd actually get something like, having both together would actually be negative. So we'd be like this. So this would be like a strong negative, this crossing of the lines. But you just let me point out, you often see in papers, this is seen as an example of a good negative interaction. If we're anywhere significantly less than parallel, and again, this is a straight line, I just can't draw very well, then this is a negative interaction, just not as strong. So here's kind of the summary from the book, from one of the textbooks I'm using. So here we have two factors A and B. So here there is no A effect. So we see that as we increase A, the response doesn't change. But we have two levels of B, and we can see that for two levels of B, level one is much higher than the other. So we have an effect for factor B. So we have one main effect, but not the other. And this is kind of the opposite. This one's a little bit awkward, but these two together are showing they're almost the same. So we say here on the x-axis factor A, it changes the response quite significantly. But between factor A and B, they're virtually the same. There's no significant difference. It'd be better if you kind of drew these on top of each other to show no difference. And here you have both factors. So you see there's a difference from level A and also a difference from level B. But the lines are parallel, so there's no interaction. And the fourth is, you can see the difference between kind of levels A. You can see that there's a difference between B, but you see these kind of lines are not parallel. So this is levels A and B with interactions. So that's just explaining conceptually what we're looking at in terms of interaction.